Inertial navigation systems calculate the position, orientation, and velocity of a moving object. These systems are used in many different vehicles, from the depths of the ocean to outer space. GNSS-aided navigation relies on a clear signal from a satellite to establish position. In contrast, inertial navigation does not need external sensors. It offers uninterrupted navigation and positioning in GNSS-denied environments. Ships are free to rotate in 3 dimensions. Inertial navigation systems measure these rotations, which are known as pitch, roll, and yaw. The inertial navigation system uses gyroscopes to assess rotation and accelerometers to sense motion. Working together, these sensors calculate the position, orientation, direction, and speed of movement for any vehicle in 3 dimensions. Gyroscopes have provided accurate measurements of orientation and angular velocity for over a century. 5 different technologies have been developed over time. The earliest systems were mechanical gyroscopes, designed by Hermann Anschutz-Kempf and Elmer Sperry back in 1904. During the 1960s, ring laser gyroscopes were demonstrated by Northrop Grumman and Honeywell. And Delco, which is now part of Northrop Grumman, developed the hemispherical resonator gyroscope. Exail developed fiber optic gyroscope technology in the 1980s. More recently, micro-electromechanical systems have been developed for lower accuracy applications. Fiber optic-based inertial navigation systems contain 3 fog gyroscopes, each measuring motion in a different axis. Making use of the Sagnac effect, fogs are passive systems that use light to calculate motion. Changes in angular velocity are measured by sending identical optical beams in opposite directions through a long fiber optic coil. The beam traveling against the direction of rotation experiences a slightly shorter path delay than the other beam. Measuring the phase shift between the 2 beams reveals changes in orientation. The performance of a fiber optic gyroscope can be changed by altering the length and diameter of its coil. Performance can be further increased by pushing back the technological limits of the optical components used within the gyroscope. This mastery of the technology means that performance levels can now be maintained while reducing the size of product units. It also means that fogs can provide unrivaled performance without multiplying sensors, unlike some other gyroscopes. Fog is the only field-proven technology that provides both outstanding accuracy and reliability. This is why more than 50 of the world's navies are already using this technology to equip their platforms, from submarines to first-rate frigates. Fiber optic gyroscopes are effective and reliable in extremely harsh environments. They operate in settings with major vibration and shocks. Their outstanding performance makes fogs the obvious choice for parts of the world where navigation is complicated, such as polar regions. They are robust at great water depths and under extreme temperature variations. This is why more than 80% of the underwater vehicles used in the oil and gas industry rely on fogs for navigation. Fogs are solid-state strap-down systems with no moving parts. This means they are silent systems and can achieve a maintenance-free working life of more than 400,000 hours, which makes them ideal for strategic as well as long-term applications such as the space industry. Fogs have logged millions of operating hours on high-profile satellite missions. Offering unrivaled scalable performance for civil and defense applications, fiber optic gyroscopes are the key to accurately defining current position and keeping everything on course.